In this section, we're going to be talking about the graphs for tangent of x and cotangent of x on the Cartesian plane. One thing you may want to consider when trying to figure out what the graphs for tangent and cotangent look like are the quotient identities for tangent and cotangent. For example, the quotient identity for tangent of x is that tangent of x is equal to sine of x over cosine of x. Meaning, if we know the values of sine and cosine at particular angle measures, then we can determine the values for tangent. For example, the value of tangent of 0 would equal sine of 0 over cosine of 0. Sine of 0 is equal to 0, cosine of 0 is equal to 1. You can use the table that I have listed here over on the left for reference for that. That means, therefore, that tangent is equal to 0 at 0, which is one point that we do have. If you try to just use the quadrantal angle measures for this, though, what you are going to find is that you are only going to ever get 0 or undefined for each of these. Because, say, for pi halves, tangent would be 1 over 0, which is not defined. At pi, tangent would be 0 over negative 1, which is 0. At 3 pi halves, tangent is negative 1 over 0, which is not defined. And at 2 pi, tangent is 0 over 1 again, which is 0. So just the quadrantal angle measures are not going to help enough to establish the graph for tangent. What we can use, though, are other points, and the most optimal ones, or the most convenient ones to work with, would be the values of pi over 4. The reason for that is because if you look at multiples of pi over 4 and evaluate tangent at that place, tangent of pi over 4 would be sine of pi over 4 divided by cosine of pi over 4. And tangent of pi over 4 is otherwise known as sine of pi over 4, or square root of 2 over 2, divided by cosine of pi over 4, which is square root of 2 over 2 again. That means that tangent at pi over 4 is just 1. Any other multiple of pi over 4, by that I mean pi over 4, 3 pi over 4, 5 pi over 4, are all either going to be 1 or negative 1, just depending on what quadrant of the unit circle you are referring to. So, when creating a t-table for tangent, if you use the t-table method for graphing purposes, it is recommended to not use 0, pi halves, and pi, etc. for those. Instead, it is recommended to use this range of values. Negative pi halves, negative pi fourths, 0, pi fourths, and pi. Or pi halves, rather. If you use these values, you're going to get one full section, as you will see, of the graph of tangent of x. And this is also going to connect a little bit more later when you see concepts concerning inverse functions. Tangent at negative pi halves and pi halves, as established before, are not going to be defined, because cosine at each of those places is 0. However, tangent of 0, as we said earlier, is 0. Tangent of pi fourths we've already established as 1, but tangent of negative pi fourths, well, negative pi fourths in the unit circle would lie within quadrant 4, and in quadrant 4, tangent is negative. So you're just going to get a negative 1 there. These values are where this middle section of the graph for tangent is coming from. You see two asymptotes at negative pi halves and pi halves. You see the points at negative pi fourths and pi fourths at negative 1 and 1 respectively, as well as the center point at the origin. In terms of the properties for tangent, the domain, this is going to be similar to the other functions established within this lesson. that there are going to be asymptotes that we need to take out of the domain. The asymptotes here are at pi halves and every pi increment after that, meaning our domain is x such that x does not equal pi halves plus pi k, where k is an integer. This is the exact same domain as secant. The reason for that is both secant and tangent, when written in terms of sine and cosine, divide by cosine. Secant is 1 over cosine, tangent is sine over cosine. So cosine is the one that causes that issue. The range, however, is not going to be like cosecant or secant, or sine or cosine. The range extends all the way down the y-axis and all the way up the y-axis, which actually means the range is all real numbers, or if you prefer to write that as negative infinity to positive infinity. This should also make sense if you consider tangent as the ratio of opposite over adjacent in a right triangle. You can have any ratio of opposite over adjacent, and that can still define a right triangle. Doesn't matter how large or small that ratio is. In terms of the symmetry, this symmetry for tangent is going to be odd, as if you take this function and spin it around the origin, it has rotational symmetry. That therefore means that if you plug in a negative input into tangent, you can apply odd identities to this, which means that you can pull the negative on the inside of the function out in front. In terms of other information, the period, this is going to be different than the previous functions, is not 2 pi. It actually doesn't take that long for it to repeat itself. For example, if you look at this point here at negative pi fourths and negative 1, the next time you get to negative 1 is actually at 3 pi fourths, which is not a distance of 2 pi later. That is just a distance of pi, which means the period of tangent is just pi. It does, though, have asymptotes, as established earlier, at pi halves plus pi k. Let's now move on into the properties of cotangent. Cotangent is going to be relatively similar to tangent. Again, we can't just use the quadrantal angle measures in order to come up with cotangent, because we're either ever going to get 0 or undefined values. Because cotangent, in terms of a quotient identity, is cosine of x over sine of x. That means that if you do values such as cotangent of, say, pi halves, that's going to be cosine of pi halves over sine of pi halves. From this table on the side, cosine of pi halves is 0, sine of pi halves is 1, meaning that cotangent at pi halves is 0, which is 1 point on this curve. If you do want to graph this, though, the t-table that is recommended to create graphs concerning cotangent, it is recommended to use this particular range from 0 to pi fourths to pi halves to 3 pi fourths and up to pi, still using phi values. At both 0 and pi, where sine is 0, we have undefined values. We have asymptotes there. And as established earlier, cotangent at pi halves is 0. For pi fourths and 3 pi fourths, cotangent of, say, 3 pi fourths would be cosine of 3 pi fourths over sine of 3 pi fourths. Cosine of 3 pi fourths is negative square root of 2 over 2, whereas sine of 3 pi fourths is positive square root of 2 over 2, giving you negative 1. This is very similar to what we saw with tangent. The increments of pi fourths, like pi fourths, 3 pi fourths, negative pi fourths, all either gave positive 1 or negative 1, because those are the instances where sine and cosine are equal to each other absolutely. At pi fourths, cotangent is also going to be 1, just like tangent, which again should not be surprising, as tangent and cotangent are reciprocals of each other. If you use these 5 values, what you will construct is this section of the curve shown, because you will have your asymptotes at 0 and at pi. You will have your values of pi fourths and 1, 3 pi fourths and negative 1, as well as where we intersect the x-axis at pi halves. The domain of cotangent, therefore, it is not going to be the same as the domain for tangent, which was such that x is not equal to pi halves plus pi k, because the asymptotes are at different locations. The asymptotes here are at 0, pi, 2 pi, 3 pi, which means that x cannot equal a multiple of pi, such that k is an integer. The range, though, is still going to be the same. The range is still all real numbers, or negative infinity to positive infinity, as cotangent would be the ratio of adjacent over opposite, which can take any shape. The symmetry, though, is also going to be odd. If you happen to spin this graph about the origin, this curve here is going to spin down such that the points up at the top are now at the bottom down here, and you have a curve that's going to still fall on top of itself. So it is going to have odd symmetry just like tangent. What that now implies is that the only functions that are even are cosine and secant. All the other functions are odd. To finish this off, cotangent will have a period as well of pi, just like tangent. And it has asymptotes established earlier at increments of pi k. To sum this content up for this section in terms of adjusting these functions, for omega greater than 0, the functions a cosecant of omega x minus phi plus b and a secant of omega x minus phi plus b will be adjusting the original periods of cosecant and secant, which is 2 pi, by taking the value of omega and dividing that. That means that those two functions have a period of 2 pi divided by omega. However, for omega greater than 0, the functions of a tangent of omega x minus phi plus b and a cotangent of omega x minus phi plus b instead will take the period of tangent and cotangent and adjust that by omega. Those two functions have a different original period of pi, meaning the new period is going to be pi divided by omega. However, when creating graphs with these kinds of adjustments, the phase shift, the amplitude, and the vertical shifts will remain the same as they did when we evaluated with sine and cosine. You can think about them in the same manner. With the period, though, do be careful based on what function you are working with.